Hello everyone. In this video we will have a tutorial session on the topics covered in module 3 of this linear systems course. So, we will do one mathematical problem followed by 3 different proofs which we have actually looked into during the lectures. So, the first problem is as follows. Let V be a vector space R2 and we are given 2 bases for R2. B which is vectors 1, 2 and 3, 4 and C which has vectors 3, 2 and 4, 2 and let small v be a vector two, 2 as per standard basis So, we are asked to find V with respect to basis B and similarly V with respect to basis C and also the change of matrix or change of basis matrix P to go from basis B to C. Okay. So, now how can we find out the coordinates of this vector 2, 2 with respect to the basis? So, when we say coordinates we can write them as a linear combination. So, I can write 2, 2 as a linear combination of the basis B. So, I will say B 1 times 1 2 plus B 2 times 3 4, okay, where B 1 and B 2 are the coordinates of V with respect to the basis B. Now, we can actually find out B 1 to be minus 1 and B 2 to be 1. You can verify this. So, which implies I will have V B is equals to minus 1 1. So, this is the representation of vector 2 2 with respect to the basis B. So, what about C? We will do the same thing with C. C 1 times 3 2 plus C 2 times 4 2 and we will get C 1 to be 2 and C 2 to be minus 1, which implies V C is 2 minus 1. So, this is the vector V with respect to the basis C. Now, we are asked to find out the change of matrix change of basis matrix P to go from B to C. So, this we have actually looked into a formula during the lectures which is given by C inverse B, where C is the matrix containing the basis vectors as columns and B is the matrix containing the basis vectors of B as columns. So, now I can get 3 2 4 2 the inverse times 1 2 3 4, okay, and this will give me, you can do the inverse by yourself. I will just give you the final answer. Minus 1 by 2 is actually the determinant, 4 and 6. Okay. So, you can verify this inverse and multiplication. So, this is my change of basis matrix to go from basis B to basis C. Okay. So, this is the first question. Going to the second question, which is actually a proof. Given two eigenvalues lambda 1 and lambda 2, which are said to be distinct of a 2 by 2 matrix A, so now we have to show that the corresponding eigenvectors V1 and V2 are linearly independent. Okay. So, we are asked to show this. So, we will go through the proof. So, to show linearly independent vectors, we will start with a linear combination as follows: A1 V1 plus A2 V2 0, where A1 and A2 belong to R. So, I am taking two scalars and writing the linear combination and saying it to be 0. Now, if V1 and V2 are linearly independent, then A1 should be equal to A2 and both of them should be equal to 0. So, this is what we need to prove to show that V1 and V2 are linearly independent. Now, we know that V1 and V2 are eigenvectors. So, I can write of A. So, I can write A V1 is equals to lambda 1 V1. Similarly, A V2 is equals to lambda 2 V2. So, consider this: A times the linear combination A1 V1 plus A2 V2 will obviously be 0, because we assumed that the linear combination gives us 0. So, now we expand it, and then I substitute these into this equation, which will give me A1 lambda 1 V1 plus A2 lambda 2 V2 is equals to 0. So, we will say this is equation 1. Now, I will consider another equation. I will just multiply lambda 1 with the linear combination, which will again will be 0, and it will be A1 lambda 1 V1 plus A2 lambda 1 V2 will be 0. So, I will call this equation 2. Now, what if I subtract 1 from 2? I will get the first terms will get cancelled out. So, I am writing only the second terms in both the equations, which will give me A2 into lambda 2 minus lambda 1 minus lambda 2 V2 is equals to 0. Okay. So, this is the equation we get. Now, we know that lambda 1 minus lambda 2 is not equal to 0, because that is the assumption that we started, that they are distinct, and then also V 2 is not equal to 0, because it is a eigenvector and it cannot be 0. So, the only way that this equation can become 0 is A 2 being 0. So, now if A 2 is 0 and I take this and substitute in the linear combination, then I get A 1 V 1 to be 0, and V 1 obviously cannot be 0. So, it again implies that A 1 should be 0. So, now this proves that A 1 and A 2 are equal to 0, and hence V 1 and V 2 are linearly independent. So, this is the end of the proof. Now, you can actually prove this for any number of n distinct eigenvalues and corresponding n eigenvectors. So, this can be extended to any number. So, now we will prove the Cayley-Hamilton theorem, which was introduced during one of the lectures of this week. So, Cayley-Hamilton theorem says every square matrix satisfies its own characteristic equation. Okay. So, this is what the Cayley-Hamilton theorem says. So, let us assume A an n by n matrix which has the following characteristic equation. I will call it P of lambda. It is an nth degree polynomial. So, say it is lambda power n plus a n minus 1 lambda power n minus 1 plus so on, a naught is equals to 0, okay, which is obviously the determinant of a I minus lambda I n. Okay. So, I will just put this as equation 1. Now, what we need to prove is that P of A, which is a power n plus a n minus 1 a power n minus 1 plus so on a 1 a plus a naught I n is equals to 0. So, this is what the Cayley-Hamilton theorem says, and we will prove this. So, the proof, we will actually take the adjoint of the matrix A minus lambda I n. So, this actually contains powers of lambda from 0 to n minus 1 and can be written as follows. Highlight adjoint of a minus lambda I n is equals to, I will take some coefficients b n minus 1 times lambda power n minus 1 as b n minus 2 lambda power n minus 2 plus so on up to b naught, where b n minus 1 Bn minus 2 B naught are all n by n matrices. So, this I will assume denoted by as equation 2. Now, if we take the formula for A inverse is 1 by the determinant of A times adjoint of A, and I can send determinant of A to the other side, and write it like this. So, I took A inverse, I put A to the other side. Now, because it is a matrix, there will be an in here. So, the same thing I can write it in terms of A minus lambda I. So, I will say A minus lambda I, this is the matrix, times adjoint of A minus lambda I is the determinant of A minus lambda I times in. So, now in this equation I will substitute 1 and 2 in adjoint of A and determinant of A minus lambda. So, then I will get something like this. This is equals to lambda power n plus a n minus 1 lambda power n minus 1 plus a naught times in. Okay. So, what we will now do is we compare the coefficients. So, when we compare the coefficients, I can write so you can actually check for yourself that when I do this multiplication, this A gets multiplied with this whole thing, and then lambda I gets multiplied with this whole thing, and then there are all powers of lambda on both sides going from lambda power n to lambda power 0, I can say, and then I just equating all the coefficients on both sides, and this is the set of equations that I get. Now, what I will do is I will multiply these with powers of A. The first equation I will multiply it with A power n, the second I will multiply it with A power n minus 1, and last I will multiply it with A power 0, which is just the identity. Okay. So, now when I do this, I will and add up all the equations. So, multiply with powers of A and add all the equations. So, when you add all the equations, actually all the terms on the left hand side get cancelled, and we will be left only with the terms on the right hand side. And what are those terms on the right hand side? The first term will be a power n, because a power n is getting multiplied with I n, and the second term will be a n minus 1, a power n minus 1, and so on a naught I n, because a power 0 is just I n, and because all the terms on the right hand side got cancelled, I can just assume it to be 0. So, now this is what the Cayley-Hamilton theorem says, and we were able to prove it. So, going to the next proof, it is another theorem which says 2 square matrices are similar if and only if they have the same Jordan form. Okay. So, we will try to prove this. So, in the first part we will take the if part, that is, we assume that they have the same Jordan form. So, if I write it in terms of matrices, if I take J1, okay, first I will write down some notation and then go to the proof. So, let A and B be n by n square matrices and let J1 and J2 be their Jordan forms. So, which means that I can write A as some P J1 P inverse, and similarly B as some Q J2 Q inverse. And you can actually see that P and Q have the generalized eigenvectors of A and B as their columns. So, this is what was discussed during one of the lectures when the Jordan forms were introduced and how can we convert a matrix to its Jordan form. So, that is what P and Q will be. So, now we will go to the proof. So, the if part we assumed that it is given that the Jordan forms are same, which means J1 is equals to J2 is equals to, I will call it J, and then I can rewrite the equations Pj P inverse and B is equals to Q J Q inverse. Now, I can write J to be P inverse A P and then substitute this in B, I will get Q P inverse A P Q inverse. So, if I take this to be R or say I will say R inverse, then I can write it as R inverse A R. Now, this implies that if I am able to write B as R inverse A R, then A and B are similar matrices. With this R is the model matrix. Now we are done with one side of the proof by assuming that we have the same Jordan form and we are able to prove that they are similar matrices. What about the other side? So if we take the square matrices to be similar, so this is say part 1 of the proof. Part 2 of the proof says that A and B are similar, which implies I can write B is some R inverse AR. Okay. So now, so if they have separate Jordan forms, I will assume them to be J1 and J2 to begin with. So now I can again say that A is P J1 P inverse. I already have that B is equals to R inverse AR, and I will substitute A in this, which implies B is equals to R inverse P J1 P inverse R, which is equal to Q J2 Q inverse, because that is coming from the Jordan form of B. Now if I compare these two, J1 and J2 are Jordan forms, so obviously R inverse P and should be equal to Q, which implies that J1 is also equals to J2, and I can again call it J. So then they have the same Jordan form. So this brings us to the end of this proof. So we have covered one problem and then 3 proofs in this lecture. So there are proofs some more like these which you can work them out, and we will try to put them out as an exercise during the course of this week. Thank you.